Hi everyone. I am showing you some exciting stuff today. I'm putting together the qualitative and the quantitative data that we've been talking about. And what you see in front of you here is the qualitative data that comes off the GOES-E satellite, one of my favorite satellites because it's so cool. And you are looking at a daytime to nighttime time-lapse animation out of the GOES satellite. And it is looking at cloud coverages, and it goes from a visual image during the day to you're seeing what's called the transition line of nighttime coming in, and then overnight it transitions to infrared imagery to keep an awareness of where the clouds are in the atmosphere. What you're seeing is you're seeing the daytime clouds, and as you transition to night, you're seeing low clouds that are blue and higher clouds that are icier and white. All right? So the low clouds that are blue, more like water vapor, more like precipitation, and the higher clouds, more like icing in that area, in that upper atmosphere. We'll learn all about that soon. This is a very cool cyclonic effect that you're seeing there in a counterclockwise spin. We'll learn all about cyclonic effects, and it's just cool to see it there tonight. I want you to take a look at the daytime and look around the Cape Cod area during the daytime and see the lower level clouds in here. I'll put in my, see the lower level clouds in here that become the lower level clouds at night. These are lower than what is rotating above them at a higher level. You realize the rotation is really in the upper atmosphere, and we'll learn all about that too. It's very cool. In addition, you're seeing the city lights of the eastern seaboard, of course, and you are starting to see some of the front lines in here as well. In terms of those front lines, I thought that I would bring you into a qualitative analysis, a surface map. And this surface map will be showing you the front lines that you're seeing there. This is actually a stationary front. We'll be learning about this. And this is a cold front through here. So when we look at qualitative data from a satellite, it can be interpreted along with quantitative data to make a qualitative analysis like this that we can see and that we can analyze a bit more. Let me stop the tape right here so I can put another slide up for you. It gets a little complicated. I'll be right back. It's an interpretation of that GeoColor satellite, the GOES-E satellite. And this will help you to understand a bit more about what you're seeing when you look on the GOES satellite. We'll actually be meeting an engineer on Zoom later on this semester who's going to tell us how he calibrated the satellite to make sure that it was depicting what you're seeing in here. So like I had mentioned to you, here's your legend here that is showing that blue is for low-level clouds at night. Right? This is the California area around San Francisco. Low-level clouds, meaning fog around San Francisco at nighttime. And the higher-level clouds and the mid-level clouds are more shades of gray to white, just as the high-level clouds during the day are white. You know about the city lights. I thought what you're seeing in here as well is you're seeing fire winds, fire smoke being driven by winds in California. So they'll give you information about thinner smoke and thicker smoke in here as well, so you can understand what you're looking at. For the next part of this, I wanted to go into the quantitative data and how that's represented. And this is a meteogram out of Morristown Airport. And what it's looking at a forecast over the next 3 days. So what you're noting in here is the nighttime through July 1st, which is grayed out in these areas. The days are white. As you can see, there's a lot more white hours during the summertime. It's a lot more daylight than gray for evening through July 2nd. And what you're looking at here, and I'm going to move this a bit, if I can move it down for you, I'm going to move it over here so you get better view. What you're looking at here is you're looking at temperature in red in Celsius. So I want to get used to Celsius. A really fast way to convert from Celsius to Fahrenheit in your head is to multiply the Celsius number by 2 and then add 30. It's really quick and fast, but what you're looking at is this. So you're saying you're 21 degrees Celsius at 8 a.m. on July 1st, on Wednesday morning. 8 a.m., 21 degrees Celsius, multiply by 2, you got 42, add 30, 72 degrees Fahrenheit. All right, that might help you out a bit. The Fahrenheit is in red. We are going to study a measurement called dew point that is in green. For now, I want you to let that ride. You also have a measurement in here for heat index. We'll be watching that over the summer. During the winter, there's actually a wind chill index in there. Down here, you have surface winds, and although this is supposed to be in International System of Units, you see the Celsius up here, the surface winds are still in miles per hour. This is part of the craziness that you're going to get for quantitative data in the United States. So we have surface winds here in purple. You see 5, 3, 2, very calm winds. And you are also seeing wind direction in here. You will be learning that the wind direction moves from the outside of the barb, the line, and into the data point. So in other words, to make it really clear to you here, this wind direction is from the north to the south to the data point. You're assuming on these mediograms that north is at the top of the mediogram, east is at the right of the mediogram, south is at the bottom of the mediogram, west is at the left of the mediogram. This is a wind that is coming from the north toward the data point at the south. This is a wind that is coming from the southwest, moving to a data point in here. And as you can see, we have got wind directions that are all over the place over the next few days. You saw in that cyclonic movement of the satellite, you're going to have a lot of unsettled air. You're starting to note the unsettled air in here and that spinning direction of the winds. You'll learn more about that. So those are your quantitative measurements for winds. Down here, you have measurements of relative humidity and precipitation potential and sky coverage or visibility. Well, sky coverage, cloud coverage, because we're talking about an airport here. So it becomes really important. What I want you to note here, just keep in the back of your head, is that the humidity is quite high during the evening hours. And look, the humidity drops off in the afternoon hours. And you're saying to yourself, oh, it is so hot and it is so humid at 4 p.m. But guess what? It actually is not that humid during the afternoons. The heat of the day actually burns the water vapor off of the atmosphere. We'll learn about why it doesn't feel that way, but that's what the data tells us, that humidity rises at night and falls during the day. On the other hand, look up here. Humidity is related to dew point. I love dew point. I hate humidity. And dew point stays very, very stable throughout the day. The temperature changes, but the dew point stays stable. That means the calculations from dew point are much easier to use and much easier to interpret. We'll get into that. Down here we have some quantitative predictions on rain levels, and they are of course in centimeters, which is kind of strange considering the wind gusts are in miles per hour. And down here we have measurements of thunder that we might interpret. Remember, it's always lightning first, then thunder. So if you're looking at what concerns pilots, if they see high thunder levels, they know that there's lightning in the area there. But that lightning is not a quantitative measure that we can put into this mediogram. We're going to be working off of mediograms and surface maps and satellite data and what we call soundings, which we'll go into later. But this is your first exposure into taking all of that quantitative and qualitative data and putting it into an analytical report. Hope you enjoyed it.